Hello everyone. Today we will learn more about the quantum chemistry. So in the second lecture, we will start with uh, Einstein's special theory of relativity. I know almost everyone have heard of this. So it states that E is equals to mc square for a photon, which is having massless properties. So in this, we can separate out the MC and C, which states that E is equals to PC. P is representing here the momentum of photon. Okay, so in this we can substitute the PC part. So we know that generally E is equals to h nu. So we have that equal to PC, and h nu is hc by lambda, which is equals to PC. Therefore, P is equals to h by lambda. So P is equals to h by lambda is for a photon traveling at the speed of light. Okay. So generally, the photons and electrons have similar nature, that they are microscopic particles, but the photons are massless and they travel with the speed of light, c. But electrons have certain mass and they don't travel at the speed of light. They travel at certain velocity, which is v. So here v is always less than c. Then comes the uncertainty principle. Uncertainty principle was given by Werner Heisenberg in 1927, and he sort of gave an idea related to an experiment. So in this, we can just imagine a slit with width W. Okay, so and we have a beam of particles. So we have a beam of particles with momentum P, and the width is assumed to be uncertainty in X. So here we are changing the width, we are increasing the width, and we are basically seeing what will happen to the beam of particles when we are increasing the width of the slit. Okay, blue, and there is a photographic plate. So photographic plate. Okay, and this is the motion of particles. So this direction we can assume it as y, and this direction is x. Okay, so we can see this spread of particles. We can see the spread of particles when it is crossing the slit. So this is the center, and we have, okay, this is the center. Assuming that it makes an angle alpha, so alpha and alpha on both sides. So we have the probability distribution as we have seen earlier, like this. Uh, okay, so this triangle, so this is the angle alpha. So we are assuming that we have two axes, so x and y, and we have a point, suppose P. This is the angle alpha. Okay, this is the angle alpha, this is the x component, and this is the y component. So this axis would be P sine alpha. So this part. So sine alpha would be this. Suppose we have AB upon this OA, and OA is P. So we have AB as P sine alpha. Okay. Now this P sine alpha we are assuming as change in or uncertainty in P. So the x-axis, so width on the x-axis represents the uncertainty in x, and the component P sine alpha represents the uncertainty in P. So when we have delta x dot delta P, it corresponds to W into P sine alpha. Okay, and P sine alpha represents, sorry, W sine alpha represents the wavelength. So lambda is equals to W sine alpha. And how this comes is, so we have this point D, assuming that this is the top of the slit. Okay, so we are assuming the point as B and this point as A. Okay, this is C. So we have alpha here. So this would be alpha, and this is half W. Okay, AB is, let's say, half W. So in this case, AD is approximately equal to CD. AD is approximately, sorry, AD is equal to CD. So we have AD is approximately equal to BD, and the half lambda is assumed to be first minimum. So at n is equals to 0. So we have the formula n plus half lambda, assuming n is equals to 0. So we have half lambda. So this is the first minimum. Okay. And BC is the part difference. So BC is equals to half lambda, which is equals to half W sine alpha. This implies that lambda is equals to W sine alpha. We have this triangle ABC, and AD is actually equal to CD, but we are assuming that AD is approximately equal to BD. In that case, in the triangle ABC, the part difference, the part difference is difference between the AD and BD. So this part difference we are assuming at half lambda. So this is the first minimum, and half lambda would be equal to BC. BC is half W sine alpha, this component. Sine alpha is equals to BC upon half lambda. Sorry, half W. Okay. Now we can say that delta x dot delta p is equals to. So delta x dot delta p was equal to p lambda. P lambda. So this is approximately equal to p lambda, and we know that p lambda is equals to h by p. So that is approximately equal to h. Okay. So this concludes that if we are narrowing the slit, so this increases the spread in diffraction pattern. So the product is approximately equal to a constant. If we are increasing the spread in x, so the spread in p decreases, and vice versa. So if we are narrowing the slit, so the spread in diffraction pattern increases. If we decrease W, so this spread will increase. So we cannot determine the exact position and velocity of a microscopic object, microscopic particle simultaneously. This is very important. If we are trying to calculate both the value of delta x and delta p, because we are trying to calculate the delta x, so we are narrowing down the delta x. In that case, the spread in diffraction pattern will increase. So we won't be able to determine the exact value of delta p. Okay. So next is, according to Newton's second law of motion, we have F is equals to ma, and acceleration is d square x by dt square. Assuming that x is a function of g in terms of t, c1, c2, because we will integrate the x twice, so these are the constants, and x should depend on time as well because it is a differential with time. So x0 would be point where g has a function t0, c1, and c2. So dx by dt would be equal to velocity, which is dg by dt in terms of t, c1, and c2. And v0 would be the initial velocity, which occurs when time is t0. So here t is equals to t0. Okay. So next we have the differential of potential in terms of x comma t as minus f x comma t. So this is potential energy. This is the potential energy V of a particle in one dimension. So particle moving in gravitational field. So it will have dv by dx. So here also it is x. So dv by dx, which is equals to minus f, which is equals to mgx. Sorry, it is equals to mg. So v is equals to mg into x. So this, when we are talking about the state of a system, these were the basics of classical mechanics, which will help in later stages. So, when in quantum mechanics, when we are talking about the state of a system, so psi, it tells that there is an existence of wave function. So this is either wave function or a state function of a particle, so of a particle's coordinates. So state of a system represents the existence of a wave function. So existence of wave function of particles coordinates. State of a system changes with time. So here psi would be a function of time. Okay. So for one dimensional, if we're talking about particle existing in one dimension, so psi would be a function of psi x comma t. Okay. So in this state, the psi, the wave function, contains all the information about a system. Okay. And for one particle in one dimension, in one dimensional system, this equation is postulated to be minus IH cross d psi x comma t. So this is capital Psi, which is a function of x and t both, del t, which is equals to minus h cross square by 2m. Here h cross is equals to h upon 2 pi. So del square psi x comma t upon del x square plus vx comma t psi x comma t. Okay, and iota here is under root of minus 1. So this equation is this equation is time dependent Schrodinger equation. This is one of the postulates of quantum mechanics, which represents a psi, which is a function of x comma t both, and their differentiation with respect to x and t, and this equation is time dependent Schrodinger equation. So according to the Newton's second law, we can basically predict the future state of a particle, where it will be with respect to time. So what will be the position of the particle with respect to time? We can predict that using Newton's second law. Uh, for so we can basically predict that, but for microscopic particles, the moment of particle with respect to time can be predicted using time dependent Schrodinger equation. Okay. Then we have the Born interpretation. What is Born interpretation? So Born states that for one particle existing in one dimension, the probability of finding that particle is square of the wave function with respect to x. So this is probability of finding a particle at time t. So particle can be found at time t in region x, lying between x and x plus dx. Okay, and The square of the wave function alone represents the probability density. So the probability of density for finding a particle at various places. Suppose that we have a region from x and x plus dx. This is in one-dimensional x axis. So the particle is lying between these 2 points. So we are constraining ourselves that the particle will be found in this region only. At that point, there can be different points at which the particle can be found. And at these different points, the chi-square represents the probability density that the particle can be found at each point of space. That represents the probability density. When we sort of integrate it over the whole region, so we will get the probability. So integrating probability density in whole region will give us the probability of finding that particle. Because it is a microscopic particle, it has both, so it has dual nature, both the particulate and wave nature. Because the particle has both nature, we cannot certainly say that particle is at one point. We cannot say that. So here, instead of calculating in Newtonian sense the particle, we use Schrodinger equation because particle has both nature. And when we are talking about the wave nature, we always use statistics to find out the region in which particle can be found. So then we have to talk about the probability rather than certainty. Okay. Suppose that we have total n systems and we measure n measurements on these systems. So dnx represents the number of measurements. Then we have dnx upon dn. Sorry. So we have dnx upon n as probability for finding the particle, which is equals to chi square dx. So therefore, quantum mechanics is statistical in nature. Knowing the state, we can't predict the result of a position measurement with certainty. We can only predict the probabilities of various possible results. Okay. Then in 1926, Dirac and John they came up with transformation theory, which sort of is a generalization of matrix mechanics and wave mechanics. Matrix mechanics was given by Heisenberg, wave mechanics was given by Schrodinger, and the generalization of both the theories is called the transformation theory, which was given by Dirac and John. Okay.